my name's Mark Hoop. I work on the same project as John and Carsten, and I have the great honour of introducing Dr. Srinivas. Yeah, I do apologise. Dr. Srinivas Vivek, yes, is currently the Infosys Foundation Career Development Chair Professional at the IIIT Bangalore. Previously, he was a research associate at the University of Bristol, and he obtained his PhD in cryptography at the University of Luxembourg. So, over to you. Thank you.
Yeah, thank you. Yeah. So thank you for the kind introduction. I'm very happy to be here. Yeah. We have been discussing about digital ID systems. Okay. Okay, sure. Thank you. So only very small population of the world have access to digital ID system. So these digital ID systems have become imperative for effective governance in many countries, including India. So we have this unique identification authority of India, so popularly known as the Aadhaar. And so we really need this Aadhaar ID so to avail many services, and it has indeed transformed dramatically how the public goods are distributed. In fact, I'll be briefly talking about its open source twin called the modular open source identity project or platform, right? So before that, so there are challenges in deploying digital ID systems, so namely the cost of setup and the maintenance, okay? And what is more important is the security and the privacy of the data, the citizens' data. Right? So MOSIP is Modular Open Source Identity Platform. It's anchored at my institute, and it's also partly funded by the Bill and Melinda Gates Foundation. So it's a digital ID platform, and as the name suggests, it's open source, and it also has this biometric identification. So it has been deployed by many countries across Asia and Africa, and also, many countries also have expressed interest. So currently, there are about 70 million people who have enrolled into this MOSIP-based system, digital ID system. And of course, so we need some trusted entities, we'll call it central servers, that securely store demographic and biometric data, okay, and they also must offer these services, right? Like the demographic, biometric, and query matching services should be, offered by these central servers, and of course, these a lot of computing resources is needed, and that calls for huge capital investment, and also under maintenance. There are also costs associated with the maintenance of this, the computing resources. Okay. Okay, and of course, so it's also advantageous to use third-party cloud services, right? Because it would be easier to deploy. It would be cost-effective, right? And also the maintenance is going to be much easier. Okay, but all is not well, and with convenience comes some privacy concerns. Okay, there are many risks associated with using third-party services. Okay, so like for instance, we should ensure compliance with regional privacy laws, and then and also, not just a third-party server. Any server is prone to hacks, right? And also, and more importantly, there could, if the third-party cloud service provider is governed, is controlled, or is accountable to another country, then the whole digital ID system could be prone to political interference. Okay, so what we present is a digital ID system. Okay, that enables the use of third-party cloud service providers, right? And we use a privacy enhancing technology called homomorphic encryption to preserve the privacy of the data that is present, that is outsourced to third-party cloud service providers. Okay, so So the technology itself will offer will guarantees for the protection of the data from third-party cloud service providers. Okay, and what is important is contrary to the popular belief that these technologies are slow and they incur a lot of overhead. So we show that biometric and demographic queries can be performed in about 0.3 seconds on a single core server. So that seems to be quite efficient to be deployable, and also the amount of space needed for the encrypted data is also like quite feasible. It's about 1 megabyte per user. Okay, so what is this homomorphic encryption? Right, it's just like an encryption scheme where you encrypt a message to get a ciphertext. Okay, and you decrypt a ciphertext when you on input a secret key, and you get back the message. Okay, but what is special about this homomorphic encryption schemes is you can compute on the encrypted data without ever decrypting it. Okay, so the third party, the cloud service providers, they will never see the original data. So they will still be performing matching on the encrypted data. So they will be providing their service, okay, but on encrypted data, and the result also will be encrypted. Only the trusted entities will be able to decrypt. So hence it's guaranteed, the privacy of the data is guaranteed thanks to the encryption. Okay, so just to pictorial represent. So suppose you have encryption of two messages, say 1 and 1, and the square represents it's the ciphertext. Okay, and you see a lock means the data is securely hidden. So you will be able to add two ciphertexts to get the sum. Okay, without actually decrypting it first and then adding and then encrypting. Okay, so with multiplication, it turns out that the moment we do addition and multiplication, we can perform any computation on that ciphertext. Okay. Sorry. Okay, so but the problem is you need to represent the whole computation as addition and multiplication operations. Okay, and then there'll be too many operations like that if you want to do any real world computation, and hence it becomes slower. So this technology is about 1,000 to million times slower than operating on plain text. Okay, so this is because the ciphertext will be so long to ensure the security, so hence it becomes so very, very slow. And the efficiency really depends on how many, what is called the multiplicative depth, means how many multiplications in series is performed. Okay, but the good news is, if your computation, if you can represent as a low depth circuit, means number of multiplications you perform in series is small, so then it's efficient enough for many applications. Okay, great. So mainly there are two such types of homomorphic encryption schemes and the corresponding libraries. One is developed by Microsoft called the SEAL, and other is called the Torus-based FHE library. Okay, so these two, the fundamental difference is how do you represent the computation. One, you can use arithmetic operations like addition and multiplication. For the other, the TFHE scheme, so you should represent like what are called the Boolean operations. I'm sure computer science this would be familiar with that, the XOR and the AND. And so the advantage of using the Boolean representation is, the comparison operations. For example, suppose we want to compare the age is above 18 or age is less than or above 18. So if you want to do these comparisons, all called the logical operations, so then the TFHE library is convenient. Now, but it would encrypt each bit, and then the amount of data that is needed to store the demographic and the biometric data would be 150 megabytes. So, but the contrary, the SEAL library, it allows us to perform, arithmetic operations. So, for example, like performing Euclidean distances between, biometric templates, for instance, those things can be done, and then we will be able to pack a lot of data into the ciphertext, about like 1 MB, right? But then we cannot do this. So we had to overcome this technical challenge. Okay, so that is the main technical contribution, where we show, using the Microsoft SEAL library that implements the BFV fully homomorphic encryption scheme, we show we can cleverly encrypt encode the demographic and the biometric data in such a way that we can avoid and overcome the limitations. So namely, we'll be able to do arithmetic operations, we'll be able to do Boolean operations. All these things become efficient. Okay. Good. So here is quickly I'll go through the architecture. So there are three entities: the service providers, like it could be like for instance, gas companies. They want to use all the digital ID service to identify prospective clients. Okay, and then the central servers, they store the original data, the enrolled, they enroll the users, okay, and then securely store the demographic and the biometric data. And then we have the third party services, abbreviated TPS. So they host the data securely, okay, the encrypted data, and they perform the matching on the ciphertext. Okay, so here is the quick setup. So we have that's trusted server is going to generate its public key and the secret key, and evaluation key is used to encrypt, do operations on the ciphertext without decrypting it. Okay, so okay, and the keys are the public keys are distributed, right? And then of course then the user will enroll into the system, giving all the data in the plain text. Okay, and then this data is encrypted, and then index into the database is generated. Okay, and then of course this index is shared with the user. So and then the encrypted data, all the encrypted data is outsourced to the TPS, the trusted cloud service. Sorry, third party cloud service. Okay, and then suppose later on when the user wants to make use of this digital ID services, so he'll go to a service provider, he or she will go to a service provider, give the demographic biometric data as is necessary, right? And then so the service provider is going to encrypt that data, right? So that the third party will never see any data in the clear. And then now that the third party will have the original data in the encrypted form. The queried data is also in the encrypted form. It's going to do matching on the encrypted data, and it's going to give the result, pass or fail, in the encrypted format. So it will be providing its services, but everything inside a black box. Okay. And then, of course, so we just need the central server to only decrypt. So of course, so every time for every request, the central server is invoked, but the work is much less. It need not do access to the database, store. All these things are gone. It can actually be stateless. Just get the data, and decryption is very efficient. Just decrypt the data and pass it on to pass on the result in the plain text form to the service provider. Okay, so this is a simple architecture. Okay, so what all data types we support? The demographic data. So these are the data like name, gender, pin code, phone number, email, date of birth. These are all encoded exactly. And then the biometric data is encoded as a finger codes template. Okay, and then yeah, as we said, we try to pack the data into only 2 ciphertexts. Okay, so it will be about close, roughly 0.9 MB is only needed. Okay, so I won't get into all the technical details. So this what you can see is the size on the disk and the way we encode. So in the interest of time, I won't get into the details. Sorry. So what we support is we support demographic matching. The name, age, everything can be compared exactly. And then we also perform threshold comparisons, as I said, like age, bigger, less than or 18, or for senior citizens also there's a need to check, right, whether your age is bigger than or equal to, greater than or equal to 65. And then biometric comparison. So this is not the first privacy preserving digital ID system that's been proposed, but it has been previously. All these things, the focus is largely on the biometric thing, but we were able to combine all this information into one system, and more importantly show that these things are efficient. Okay, so to be deployable in practice. Okay, great. And then so we see that we just need 0.3 seconds for the biometric matching. That is the most expensive operation. And for the demographic query matching, it's just like few tenths of milliseconds. Okay, and these things are all on a single core. Of course, these things can be accelerated if we, also opt for hardware acceleration, hardware implementation. Right? Of course, so we assume that all the players are honest, means they perform their computation, but the trusted party is curious to learn the data, and we need, and our system is compatible, to deploy additional strategies to prevent data leakages, in case of there are active attacks by the entities, right? Then, okay, so I think that's briefly our work. So this was funded by the MOSIP project, right? And then we also like to thank the MOSIP team for the valuable discussions. Thank you.
A hot topic there, so it was a great talk. Thank you. Got a couple of questions. Still there? Yeah. So the top one, the cost of the FHE. Can you provide a couple of use cases around this area for us?
Oh, good. Yeah, okay. Yeah, that's a very nice question. Of course, we are not using the fully homomorphic encryption because of the fact that we can use partially homomorphic encryption, so namely the additive homomorphic encryption for the case of only demographic query matching. All right, but here we are doing both multiplication and the addition operations. So hence we need fully homomorphic encryptions, but it need not be fully. It's what is called a somewhat homomorphic encryption. We just need to support limited number of multiplications. So that's what I mean. Yeah. So we really needed that in order to support different query types.
Just limiting the size of the query you're talking about. Sorry. Sorry. You're limiting the query. Did you say sorry?
No. If we use the partially homomorphic encryption scheme, so then we have to limit the query type. But because we are using a fully homomorphic encryption, so we could support different types. So including the demographic matching, the threshold matching like age bigger than or something value, and biometric matching. We could support all these things because we used a fully homomorphic encryption scheme.
Okay, fascinating. We'll have to talk more about that. Thank you. Okay, thanks once again.